Okay, so we'll begin. Are there questions?
Yes, sir.
Yes, go ahead, please.
Could you go back to page 209?
209. Yeah.
Yeah, so the expression that we have for G, just a little above.
Yeah.
Yeah, here we are basically expanding something like 1 by 1 plus x or 1 by 1
Yes,
minus x
that's right.
if you
Yeah.
may.
Yeah.
So
Exactly.
apart from the divergences present in sigma, shouldn't we also worry about the radius of convergence of the perturbation series?
Yeah, we should accept that because sigma has a coupling constant already, right?
The lambda.
Lambda. You by definition you expand in powers of lambda, right?
Yeah, but that expansion should be finite in the sense that since at the end lambda is a number.
Yeah, but the point is when you do perturbation theory, you don't worry about convergence of the perturbation series because it's known that in most quantum field theories, this perturbation series in fact is not convergent. It's asymptotic.
Yeah, so what are we trying to do here then? Like, are
Yeah,
we going?
the point is asymptotic series still works quite well, right? Okay. So what does asymptotic series do? That it says that if lambda is sufficiently small, right, then the series will give the result that is close to the actual result, okay, up to a certain order. Okay. But then if you keep expanding beyond that order, then it will go away from the actual answer. Okay. And typically that order is controlled by 1 over lambda, right? If lambda is small, then we can go up to say order 1 over lambda. Okay. And it's also like this here. Okay, typically all quantum field theories, as I said, have asymptotic series. Okay, you can see. I mean, there is a good reason why we know that this cannot be a convergent series. I mean, convergent in the sense that so by asymptotic, one means that even the radius of convergence is 0, right? It's not that it's like 1 over 1 plus x, because there we can say, okay, as long as x is smaller than 1, you can the expansion converges, right?
Yeah, but it's already infinite in the sense that sigma is already infinite.
Yeah, but that problem you can't avoid, right? But because as I said, that here it looks like sigma is already infinite, but there is a way to reorganize this perturbation expansion so that you expand in parts of renormalized coupling.
Yeah, but even so, in the renormalized coupling, we should be worrying about radius of convergence or not?
Yes. So you should worry about radius of convergence in renormalized coupling, but at least this ultraviolet divergence problem is not there.
Yeah.
Renormalized coupling. Okay.
Like, shouldn't we be making some definite statement here regarding even the renormalized coupling? That after the factor should be like modulus of the factor should be less than 1 for this series to be like giving a pole like this.
Well, the point is, if you want to find that analog of the 1, it is actually 0. Right? Because e to the minus 1 over g, as I said, has no expansion, right? Its expansion in powers of g will be 0 to all orders, right? If you try to expand around g equal to 0, because all the derivatives actually vanish if you start from the g on the positive side.
What are we expanding again?
E to the minus 1 over g.
Okay.
Or e
And
to the minus 1 over lambda in powers of lambda.
okay.
So if you try to calculate the Taylor series expansion coefficients, right, by taking derivatives and then taking lambda goes to 0, all derivatives are 0.
Yeah.
Right? But nevertheless, e to the minus 1 over lambda is not a zero function, right?
Yeah.
Okay. So this is the example of an asymptotic series. So asymptotic series has this property that that the radius of convergence may be 0, but nevertheless, what you can say that as long as the coupling constant is sufficiently small, the expansion makes sense, or if it's close to the accurate result, the actual result, okay, up to a certain order in expansion in powers of lambda. And then if you try to go beyond that order, you get there is actual result starts diverging from the original, the perturbation expansion starts diverging from the actual value.
So my main concern here is that suppose we are calculating scattering amplitudes and these are physical quantities, so we can confirm with experiment.
Yes.
Now suppose I take this 5-4 theory and try and describe an electron scattering, electron scattering
Yeah.
sort of thing,
Okay. So that's of course not
hypothetically.
5-4 theory. That's QED, say, right?
Yeah,
But
yeah. The correct theory would be that.
yeah.
But suppose I don't know anything about the quantum field theory in the sense that I don't know which equation to use for which
Okay.
particle.
Yes.
So I am just trying to fit in the sense that I'm trying to find a theory for some given particle.
Yes.
So I try the 5-4 theory and it should be incorrect in the sense that some scattering amplitude should not match with the theoretical result.
Yeah.
So at that point, should I question my equations or should I question this radius of convergence thing? My
No.
perturbation expansion, like,
Okay. So the point is, as long as the coupling strength is small, right? By doing a measurement in electron scattering, you know that the effective coupling is small.
okay.
Okay? And the value of the fine structure constant is 1/137, right? So one expects that whatever theory it is, up to 137th order, or say 100th order, right? I mean, it's not exact. Up to 100th order, the actual perturbative results should become better and better to the actual answer, up to say 100th order in perturbation theory, and then it will start diverging, right? Then it will start going away from the actual result.
Yeah.
So then suppose you try to say that 5⁴ theory is the right theory. Okay.
Yeah.
And you use the coupling strength to be this 1/137. And then you will discover that the first few orders in perturbation series does not give the right answer.
I mean, here also we are sort of like, well, not assuming, but we already know that the coupling is alpha, the fine structure constant. But in a new experiment, let's say we have a new particle, and I don't know what that means, but let's say we have an unknown particle,
Yeah.
and we are trying to write down an equation for that, a quantum field theoretic model for that.
Yes.
So we'll try different fields, scalar field, maybe spinor, I don't know how the phenomenological procedure is, but regardless of whatever we try, we'll have to match out the scattering amplitudes. And in order to do that, we need to sort of correctly estimate how to write G tilde, the
Yes.
correlation function.
Yeah.
So I'm saying that it might be possible that our results are not matching because we have not correctly calculated G tilde. Maybe we have not taken sufficient terms, or maybe we have taken too many terms.
Yeah. But the point is that the tree level, you can first try to match the tree level result, right? To get an estimate of the coupling. See, if you are saying the theory is strongly coupled and hence you cannot do perturbation theory at all, that's certainly possible, right? There may be theory that a new particle may be genuinely described by a strong coupling theory, right?
So right now, I'm not sure what strong coupling means. Like, how do we qualify what is strong, what is weak here?
Yeah, just do scattering, right? A scattering cross section, okay, which we'll do eventually, and see how much is the scattering cross section, and that will give an idea of what the coupling strength is, right? With what strength the particles are scattering each other, because the scattering cross section is controlled by the coupling. Okay?
Are you saying this can be evaluated without actually going into the details of the theory?
Well, it can be evaluated. The order of magnitude estimate can be evaluated without going into the details of the theory. So that's just tree-level result, right? And the propagators give some kinematic factors.
Okay, yeah.
So you can get an estimate of the coupling, of the strength of the coupling, before knowing the details of the theory. And then, of course, you have to go to the details of the theory to explain the full scattering results. So if the theory is not weakly coupled, then of course all these techniques will not work, right? You have to find new technology to describe the theory. And there are strongly coupled theories of this kind, right? QCD, for example, is strongly coupled, so you cannot use the standard perturbation theory to describe strong interaction.
Okay.
But when the interaction strength is known to be weak, then you can try to do this, right? Just by having an estimate of the coupling strength, you know to which order it will work, right? And of course, I mean, we don't calculate to that order, right? I mean, nobody has calculated up to 100th order in quantum electrodynamics. Right?
Then
Typical,
what is the like? Shouldn't we be calculating though?
well, the point is the calculations become more and more difficult, right?
Okay.
I mean, people have gone up to maybe 4 loops in some very specific calculation. Right?
So 4 loops is also a huge number in that sense.
No, four loops is huge. Huge number in what sense? The actual value is huge.
I mean, 4 is a lot. Usually people don't calculate up to 4. Are you saying that?
Yeah, exactly. I mean, in QED, for example, 4 is a lot because the number of diagrams keep increasing, right?
Yeah, I get that complexity part.
Yeah.
But in actuality or numerically also people don't.
No. I mean, I think G minus 2 people calculate, but that's up to, I mean, 5 loop, maybe some people have attempted, but I don't think the calculation is complete yet.
But the results like CERN super collider results and all these results agree.
Yeah,
Still.
they agree quite well. Because
Isn't that
experimental
strange?
accuracy, upon if you think of 1 over 137, right? And if you go to fourth order, it's a lot, right?
I don't know.
Meaning 1 in 10 to the 8, right? That kind of accuracy is hard to achieve in experiments.
Okay.
Right? In some you can, right? G minus 2 is very accurately measured. That's why, I mean, that the theory and experiments are competing. Yeah, right now I think the theoretical error and experimental errors are more or less on the same ballpark.
Okay.
Yeah, so typically you don't have, I mean, in the weakly coupled theory, right? In QCD, of course, you have to go to higher, I mean, you have to do a resummation and do various tricks. But in electromagnetic and weak interaction, right, you don't go to very high orders.
All right.
Okay. Are there other questions?
Yeah, hello, sir.
Yes, but
can you go to the expression of A dagger in that you defined last time?
expression of
A in dagger and A out dagger.
A in dagger and A out dagger. Okay, let me. Yeah, I think this is the expression for A, right? We define.
I can do with that.
Okay.
Yeah, so A in dagger was defined for T going to minus T times 1 minus I epsilon.
That's right, yes.
So it could be that this operator is not well defined. I mean, it could give some good answers for some states, as you showed for in states P1, P2 up to Pn in. It adds some other momentum state to that state. But if I had written, let's say, A in dagger some out state, acting on some out state, it might not have given us some like definite answer. It could have blown up.
Yeah, it could.
That could have been possible.
That is possible, yes. So normally we don't try to apply A in dagger on out states, right? But typically what happens is the out basis, right? Because S matrix basically expresses the out states in terms of in states, right? Because it's the inner product between the out state and in state.
Yeah.
So once you know A in dagger on in state, right, you can calculate in principle the A in dagger on out state by re-expressing the in state in terms of the out states using the S matrix.
Yeah, I mean, that's what I'm saying. It might not be like well defined.
It may not be well defined in the sense that the sum may blow up, right? If you are thinking of because in state, when you express an in state in terms of out state, right, it has infinite number of, you have a sum over infinite number of states, right? And it could blow up. Yeah. But we don't try to apply A in dagger on the out state.
Okay.
Right. So, I mean, this is part of the postulates of quantum field theory, right? I mean, the point is that, as I said, we cannot derive it starting from first principles. So what we do is that you make some ansatz of how the theory works, and then you check the internal consistency, right? And what happens is that which in the process of checking the internal consistency, also learn how to get the result, assuming that these are true. Right? Just like we got the expression for the S matrix, assuming these forms of A in dagger and A out dagger, but we didn't really rigorously establish that these operators exist, for example.
Okay.
So that's part of the philosophy of quantum field theory, the way it works, right? That you really don't solve the theory starting from first principle, at least except for maybe for simple quantum field theories, right? There are some solvable models, but in a generic case, right, these you take as ansatz of quantum field theory or axioms of quantum field theory.
Okay.
Yes.
So far, there is nothing that really tells us that we must have single particle states in any arbitrary QFT.
Exactly. Yeah.
Interacting QFT, especially.
Yeah.
In free QFT, we can still somewhat interpret some states because we have the direct exact information of A and A dagger.
Yes.
So we can interpret the states acting on vacuum as some single particle, multi-particle states.
Yes.
But in interacting theory, there is no given notion, predefined notion. Right now, also we are working with a assumption that let there be single particle states, and that will have mass MP.
Exactly.
So, like, suppose in a real world theory we do not have single particle states. When will we realize this?
Well, I mean, we know experimentally that there are single particle states, right?
But that is not an argument, right? I mean,
yeah, well, the point is that's why I said that you in quantum field theory, right? I mean, unless you can actually solve the theory exactly, right, you cannot establish that these states exist, right? But assuming that these states exist, you can get a consistent formulation, right? You know how to calculate the S matrix. The point is you can get some numbers out of these assumptions, right? I mean, these assumptions are not that you are assuming that this S matrix is this, right? But you assume existence of certain states. And based on that, you then proceed and you find that you can actually get some numbers out of it, which you can test against experimental measurement.
But let's suppose I have a kind of particle I have a kind of theory rather, which does not allow single particles. Maybe it only allows a couple to be present at the same time.
Yeah, it's possible.
I cannot frame this precisely, but
yeah. So conformal field theories, for example, are that kind of theory.
What kind of theory?
Where you don't have single particle states, right? You don't even have a notion of particle states, right? Or S matrix.
Yeah. So what are we calculating in those cases?
Well, in those cases, you calculate different things, right? The Green's functions. See, the Green's functions, of course, are the basic objects.
Yeah.
Right. And in conformal field theory, the way you will make connection between the theory and experiment is different, right? It still starts with the same Green's function.
Okay.
But you do the actual experimental measurements are different, right? You don't scatter because there is no particle to scatter.
Yeah.
Okay, but you measure something else, like in statistical mechanics, for example, all the scaling laws, etc., come from properties of those Green's functions.
Okay.
So depending on the situation, right, you can make use of the same Green's functions in different ways. Right? Here, what I'm describing is a particular realization of the quantum field theories, where there are single particle states. And once you have the single particle states, you can scatter them and you can ask what happens. And that's what the S matrix theory gives us.
Okay. And also one last thing, for zero mass, let's say scalar particle, the MP is 0, right?
MP is 0.
But M could be something like there is some M and there is some coupling lambda.
Yeah. M could be for something, right? Unless there is some kind of symmetry, right, which says that MP equal to 0 means M is equal to 0. In general, it's not true, right? So M could be anything. Right?
So I can, like in principle, I can try and describe photons also with some 5-4 theory or something like this.
No, because we'll see that the photons have very specific property, right? That which basically tells us that M is not normalized. So for photons, the unrenormalized mass is 0 as well as the renormalized mass is 0.
Okay.
So you couldn't describe photons by, it's first of all not a scalar,
Yeah.
right? And yeah, so photons have very specific property, right, which tells us that the mass is not renormalized.
Okay.
Any other question? Okay, so let me then begin. Okay. So what we found in the last lecture is an expression for the S matrix. We saw that it can be related to the Green's function. Okay, in fact, this was the final result that we got. Okay, in terms of the amputated Green's function, where we just remove the external 2-point functions. Okay. But this was based on certain assumptions. Okay. And these are the assumptions that we use to get that form of the S matrix. Okay. And basically, these assumptions can be summarized by saying that A in dagger and A in acts as the creation and annihilation operators for the in states, okay, and A out dagger and A out acts as the creation and annihilation operator, the opposite A. So A out and A out dagger, okay, acting on the left, acts as the creation and annihilation operator for the out states, okay, which is here. So what we'll try to do today is to justify these relations, right? How did we come up with these in the first place? So is this okay? These are the relations we used, if you remember correctly, in the last lecture. Okay, so these are the relations that we'll try to establish today. Okay, and see what goes behind actually establishing these relations. Okay, so let me begin by reminding you of some definitions. Okay. So we define a dagger, okay, as a function of t and p by this relation over here. Gp I have given later here. Okay, so this was a very explicit function, plane wave with a certain normalization. So that was the definition of a dagger. Then in terms of this, we define the A in dagger. We divided by this 1 over root z factor. And then we took the limit in which the argument goes to minus infinity. The time argument of A goes to minus infinity. And with also this 1 minus I epsilon. So you want to prove that A in dagger acts as creation operator. But first, we will begin with the simplest case, where A in dagger act on the vacuum. And our goal will be to prove that A in dagger acting on the vacuum produces the single particle in state, which is of course the same as a single particle out state. So for in single particle states, you don't distinguish between in and out. Okay. And this 1 over square root of 2 EP is the normalization, because we have normalized this so that its norm is 2 EP times delta P minus P prime. And that's where this 1 over square root of 2 EP comes from. Okay. This also was present here. Okay. This was the form. Okay. So this is what we'll try to prove first. Okay, so to prove this, let's first begin with ATP dagger on the vacuum. Okay, and then we'll take the appropriate limit and divide it by root z. So we rewrite this by inserting a complete set of states here. Okay, so this is sum over alpha, complete set of states, A dagger on vacuum. Okay. And now I'm going to use the expression for A dagger that is given here, and use the fact that these states, basis states, of course, we are using the Heisenberg picture. So the basis states are time independent. Okay. So this time derivative part, we can just take out of the states. Okay, so you can just apply this, you can put it anywhere because these states do not depend on time. Okay. So this was acting on phi. Okay, now we have taken it out, so this acts on a matrix element. Otherwise, I think I have not changed anything. Thus, I have brought to this side as minus I, integral dq bar gptr, and then this. Okay, so is this clear so far? Okay, So now let me remind you of a relation that we had derived earlier, okay, that the matrix element of phi tr between any state alpha and the vacuum, okay, is given by this, that RT dependence. Okay, the way we had found this, if you recall, is that we use the fact that the P mu commutator phi is I del mu phi. Okay, so that gave a differential equation for this, because P mu commutator phi on the one side it gives you P alpha, on the other side it gives you 0. Okay. So that gave a differential equation for this, and by solving that we got this result. Okay, that is given by to the R and T dependencies are simply given by this formula over here. Okay. And now let me also write down the form for GP, okay, which is this plane wave with this normalization. And now you see that we can evaluate this explicitly. Okay. So first of all, the R integral. Okay, let's look at the R integral. Okay. So there is one R dependence coming from here e to the minus I P alpha dot R. Okay. Another R dependence coming from e to the IP dot R. Okay, no other R dependence. So the R integral simply gives 2 pi cube delta P minus P alpha. Okay, from this product. This derivative acts on both sides. So when it acts on the right, it acts on this, so it brings out a factor of I times E alpha. When it acts on the left, it brings down a factor of minus IEP. But of course, that when acting on the left, there is an explicit minus sign, right? Because it's like G times derivative of phi minus phi times derivative of G. Okay, so that minus sign cancels this minus sign, and you get a factor of I times E alpha plus EP. So putting all these results together, okay, we get this expression. Okay, we can write this expression in the following way. So it's minus I is minus I. Inside GP, there is 1 over 2 pi to the 3 by 2, 1 over square root of 2 EP, which I have written explicitly. E to the IP dot I have not written because that got converted to this delta function. So there is a 2 pi cube and then delta Q of P minus P alpha. Then you have this I times C alpha plus EP, okay, which I have written here. Then the exponential of the time dependent parts, e to the I E alpha t and e to the minus I EP t, which is here. And then this state alpha and this matrix element, okay, which is what I have written. And these two have written in red because they just cancel, right? Minus I times y gives you 1. So this is the expression that we'll now try to manipulate. Okay, are there questions? Okay, so let me then proceed. Okay, so this is the same expression as what I wrote here, okay, except that I have cancelled this minus I and I. So now let's recall that we have to set this time to minus t times 1 minus I epsilon and then take the t goes to infinity limit. And then also multiply by 1 over root z, okay, because A in dagger, let me remind you, A in dagger expression had this 1 over root z and then this limit. Okay. So let's first see the effect of setting t equal to minus capital T times 1 minus I epsilon. Okay. So that t dependence is here. Okay. So it becomes e to the minus I E alpha minus EP times t. Okay. And then the epsilon, right? So there is a total I epsilon, right? It's minus sign and minus sign gives you I epsilon. So I times I gives you minus epsilon, minus 1. So you get minus epsilon times t and then E alpha minus E, okay, which is here. And now we see that because of this factor, as t goes to infinity, the dominant contribution comes from the lowest value of E alpha. Okay, because it comes with a minus sign, right? So lowest T alpha gives dominant contribution in the capital T goes to infinity limit. So what is the lowest T alpha state in our theory? Of course, it's the vacuum, okay, by definition. But the vacuum cannot contribute because vacuum has 0 momentum, right? Because P alpha is 0 for the vacuum. Okay, if you choose the state alpha to be the vacuum, it has 0 momentum. Then this delta function will make it 0. So the vacuum is not allowed. So you pick the next best choice, which is a single particle state. Okay, single particle states do carry momentum, and we can choose P alpha to be P. And it's clear that as t goes to infinity, all other states can be ignored because of this factor. Okay, for single particle state, this factor will vanish. But for any multi-particle state carrying total momentum P, this E alpha will be larger than EP, and it will be damped out. Okay, in the t goes to infinity limit. So we replace this sum by sum over single particle states. But if you remember, for single particle states, we had seen that the sum over alpha basically becomes integral over d cube q. And with the normalization that we have chosen, it's actually integral d cube q over 2eq. This is the Lorentz invariant integration measure. Okay, in fact, this is the reason, because we wanted to write the integration measure in this way, we chose the normalization so that there is an EQ, 2EP factor in the inner product between P and P prime. So we'll replace this sum over alpha by this integral dq of d cube q over 2eq. This P minus P alpha will be replaced by P minus q. This will be replaced by EQ. This will be replaced by EQ. Okay, and this is now a single particle state, which we'll be calling QQ. But we had also seen that this matrix element, single particle state phi 0 omega, is given by root z over 2 pi to the 3 half. Okay, if you don't remember, if you can go back and look at the analysis of the 2-point function that we did, right? And we picked up the contribution from the single particle states to see the pole, and there we had introduced this constant z by this identity. Okay, we had first proved that this matrix element is independent of q, and then whatever constant it is, we had called this z over 2 pi, root z over 2 pi to the 3 half. Okay. So we are going to now substitute this in this expression. Okay, are there questions? Okay, so if not, let me then proceed. So we are going to substitute this here. Okay. So let's see what we get. Okay, so A in now we are talking about A in dagger on vacuum because we have already made these replacements. Okay. So we start with the 1 over root z factor, right? Because the definition of A in dagger has this 1 over root z. Then these factors remain as it is, 1 over 2 pi to the 3 half, 1 over square root of 2 EP, 2 pi cube. So which is all I have written here. Then the sum over alpha here becomes integral d cube q over 2eq. This delta function becomes delta q of p minus q. Then we have this eq plus ep. Okay, that's this factor over here. And this exponential factor, let's see what it becomes. It's e to the minus I times t times 1 minus I epsilon, then now eq minus ep, because E alpha has been replaced by ep. And finally, this matrix element, which I have replaced by root z over 2 pi to the 3 half. And now we see that most of the things cancel. This 2 pi cube cancel this 2 over 2 of the 2 pi to the 3 half factor from here. The root z gets cancelled by 1 over root z. That comes in the definition of A in dagger. This q integral is done easily because q is set equal to p. Okay. So that gives you 1 over 2 ep, but that gets cancelled against this 2 ep factor that comes from here. Okay. This becomes just 1, right? Because eq and ep are the same. And this q is replaced by p. So we arrive at this expression over here. And this, of course, is exactly what we wanted to prove, right? That A in dagger on the vacuum creates a single particle in state, okay, which in this case is also a single particle out state. Okay, because for a single particle, there is no difference between in and out states. Okay, and this 1 over root 2 EP factor comes out naturally from this. Okay, are there questions? Okay, So I'll proceed. So next, let's try to prove the reverse relation. Namely, A in should act as the annihilation operator. And here we are going to proceed more or less in the same way. So we want to prove that A in of P acting on P1 in state is given by this combination over here. So for this, we start by looking at the definition of A in. So A in is related to A of T on P. So that was defined by this relation over here. Okay, here you have a GP star instead of GP and minus I instead of I on this side. And A in of P is given by 1 over root Z times the same limit. Okay, but this time out with A instead of A dagger. So we'll now again write A on P1 in state as given by sum over alpha, okay, times a complete set of states. Then ATP on P1 in. Okay. And at the end, you have to keep in mind that the T you have to set equal to minus T times 1 minus I epsilon. Okay, so now again, we use this expression, okay, with I integral dq bar GP TR star. Okay. And then as before, you have taken this derivative outside the matrix element. Okay, so this comes first and then you have the sum over alpha times this. So this is something that you hadn't seen before. Okay, but this can be easily evaluated, okay, by using the same trick that we used for the vacuum on one side. So we use the fact that the commutator of P mu with phi is given by I times the derivative of phi. And using this, we can write a differential equation for phi for this matrix element, because this tells us that I times this derivative. This derivative, of course, you can take inside, okay, because these are space-time independent. So you get alpha P mu commutator phi times P1. But then this is just P mu phi minus phi P1, P mu. So P mu acting on the left gives you P alpha mu. P mu acting on the right gives you P1 mu. Right? So you get P alpha minus P1 mu times this. Here you should remember that P1 0 is not independent, it's just EP. Right? Because this is a state whose momentum is P1 and energy is EP1. Okay, so P1 0 is EP1. So this is a differential equation for this matrix element. So you can now integrate this differential equation to get the matrix element of phi between alpha and P1 as e to the minus I P alpha minus P1 dot x. Okay, because this minus sign comes because the I goes on the other side, putting a minus sign. And this is the initial condition, because when this you set this equal to 0, of course you should get back the matrix element of phi 0 between alpha and P1. So this is a boundary condition, and then this is the solution. And here what I have done is that I have just expanded this out in the space part and the time part, okay, with the same matrix element. Okay, is this clear? So this takes care of this term over here. And now I'm going to substitute the expression for GP TR star. Okay, which is, yeah, this is just a complex conjugate of the GP that I showed you last time. So let's now put this back here. So this gives us the expression for ATP on P1 in. So this part is the same, I times integral dq, but here I've substituted for GPTR star this whole expression, okay, which is here, okay, up to this point. Then you have this 2i derivative, and then here instead of this I have written the actual space-time dependent factor. Okay, I have basically used this expression over here. Okay, so this is a space-time dependent factor, and this is just a constant. Okay, doesn't depend on T or R. Is this clear? Now again, we perform the integration over R. So let's see where the R dependence is. So there is a e to the minus I p dot r. Okay, this is coming from GP star. Okay. And then you have this e to the minus I p alpha minus p1 dot r. Okay. So together this gives you a delta function 2 pi cube delta p plus p alpha minus p1. Okay, so that's this delta function over here. Then the derivatives, the two-way derivative, let's see what factor it brings. So acting on this, it brings down I times E alpha minus EP1. And acting on this, it brings down I times EP, but of course with a minus sign because the derivative is acting on the left. So that gives you I times E alpha minus EP1 minus EP. And I think the rest of the factors are exactly what you have. So let's say I is here, then 1 over 2 pi to the 3 half 1 over 2 square 2 EP. This 2 pi cube came because of this. Sorry, this should have been a 2 pi cube. So this 2 pi cube came from here, the delta, this delta function. Then the delta function, then this factor of the energies. And then I have written the t dependent exponent, okay, including these two factors, and then the matrix element. Okay. So this then is the final expression for A that we get. Okay. And now we are going to make this I times I into minus 1. Okay, are there questions?
So for a moment, could you go back to the previous one, the A dagger on vacuum, and where we have stated that the minimum contribution comes from the single particle state?
Yes, okay.
Under the limit, yeah. So here, if I had a theory with mass 0,
Yes.
multi-particle states could also have the similar energy, right?
Yeah. So if I mean here, of course, you have assumed that the single particle state is the lowest mass single particle state, right?
Yeah.
So what you are saying is if it so happened that the state that we have that we're looking for, right? If there is another set of particles which has energy below that state, which has mass below that state, it could be that two particle state of the other particle would be lower energy. That's what you are asking, right?
I was saying something like a linear dispersion relation in energy.
So massless case is a special case.
Yeah.
Massless case, any number of particle state has energy less than the energy of the original particle.
Yeah.
Right? Yeah. So in that case, of course, those contributions will also have to be taken into account.
So we won't have a single particle creator operator.
Yeah. So the point is, typically in that case, what it means is that the single particle states are not stable, right? Because if it's energetically possible for the single particle state to decay into multi-particle states, it will decay.
Okay.
So the in states, strictly speaking, in states refer to stable states, right? States which cannot decay into anything else.
All right.
Now, it could happen that even if there are multi-particle states, some symmetry reasons prevent them from appearing.
From vacuum.
Yeah, from the vacuum. Okay, so I'll give an example. So, take electrodynamics. Okay, of course, you have not done electrodynamics. Okay, but I think you can see this. That suppose you are trying to look for the A dagger that you are talking about is the A dagger for the electron.
Yeah.
Okay. So you have to apply the electron field, or the analog of the phi will be the appropriate phi for the electron, right?
Yeah.
Now this theory also has photons, okay, which are massless. So the same problem might appear here, right? You may wonder that how come multi-photon states have lower energy, right?
Yeah.
But what happens is that in that case, the electron operator, right, or whichever operator creates this electron, right, with the analog of phi, will have the property that its matrix element with the multi-photon states will be 0. Just because it carries some conserved charge and multi-photon states don't carry the conserved charge.
I see. Yeah.
Okay. So that can happen, but if there is no conservation law, right, that prevents the multi-particle state from appearing in this channel, right, that basically says that the single particle state for which you are trying to construct the in state is actually unstable.
All right.
Okay, are there other questions? Okay. So we'll now proceed from here. Okay, this is the expression we had arrived at. Okay, so this is the same expression as before. And now again, let's recall that you have to set this time to minus t times 1 minus I epsilon, and then take the t to infinity limit and multiply by 1 over root z. So again, we analyze the exponent, okay, because that's what tells us which state will contribute. So if you look at the exponent and substitute this, okay, you get this phase factor, but there is also this real part, right, which is t epsilon times minus E alpha minus EP1 plus EP. And again, because of this minus sign over here, it's clear that it's the lowest energy state that's going to give the dominant contribution. Okay, here. So you have to look for the lowest T alpha state. And now the lowest T alpha state could be vacuum. Okay, and indeed it is the vacuum. Because if you put a vacuum here, this matrix element is non-zero. Okay, this delta function doesn't prevent the vacuum state from appearing here, right? Because for vacuum, of course, this is 0, but you have a delta Q of P minus P1. Right? That basically means that you will have this delta Q of P minus P1. So the dominant contribution this time comes from the vacuum. And if you set this equal to vacuum, then you get this as the e to the minus I times EP minus EP1. And this becomes delta Q of P minus P1. Okay, is this clear? So basically what is going to happen is that because of this delta Q P minus P1, we can set EP equal to EP1 everywhere else. Right? So this exponent just disappears completely, right? E alpha becomes 0 because alpha has been chosen to be the vacuum. Okay? And then now EP1 becomes equal to EP, so the exponent again completely disappears. Things simplify, and also this matrix element now becomes the matrix element of phi 0 between the vacuum and P1. Okay? That again is root z over 2 pi to the 3 by 2. So let's see what we get at the end. So A in P on P on N. So first of all, in the expression for A in, there is a 1 over root z. So let me write that first. So there's a 1 over root z. Then you have I up to this point. I'll just write the same factor. I times 1 over 2 pi to the 3 by 2, 1 over square root 2 EP, 2 pi cube. Then the sum over alpha has gone. It says one state vacuum. So this is delta Q of P minus P1, right? Which is what I have written here. This now this is 0, right? And EP1 I can replace by EP. So this just becomes I times minus 2 EP. That's what, well, I have not written it here. So it's I have still written it as EP1 plus EP, but this is really 2 EP. And then finally this exponent has gone away. The state is a vacuum, and this one gives you the root z over 2 pi to the 3 by 2. Okay, so that's what I have written here. And at the end, now if you cancel everything, right, this I and minus I gives you 1, this gives you 2 EP, which cancels against the square root of 2 EP to give a square root of 2 EP1. P has been set equal to P1. And the 2 pi cube cancels. And at the end, we get the desired relation, right? This is exactly what we wanted to prove. So we see that indeed A in does act as an annihilation operator, okay, acting on the state P1 in. And you can also convince yourself that A in on the vacuum gives you 0. Okay, basically what will happen is that the lowest state now is a single particle state, but for that, this exponent just gets damped. Okay, so you get 0. Okay, are there questions? Okay, so you have proven the two relations that you wanted to prove. Okay, but now we have to look for the general case, right? How to prove this in general. So basically the general result can also be stated in this way. that if we apply n of p1 dagger n times on the vacuum, right, with different p's, then you should get the multi-particle state with momentum p1, p2 up to pn. Okay? And these are the normalization factors that should come with n p1 dagger. Now, what do you mean by this? Right? So for this, you have to recall what is the definition of this in state. So the definition of the in state that we gave is that if we multiply this in state by this product of this form, with Fi tilde being this Gaussian, then this state, this times the above equation, so that means the in state, when you evolve it in time, okay, to the past, right, to the far past, that means to large negative time, using Schrodinger equation. Then, if this was really the in state, then this should describe particles, n particles with momentum k1 to kn, which move along the trajectories Ri equal to kit, and the momentum space wave functions of those particles should have been given by this. Okay, that's the definition of what we mean by in state, right? That in states are such that when you evolve, when you first take the convolution of the in state with this, then evolve it using Schrodinger equation to a large negative time, then it should look like individual particles, okay, which are moving along well separated trajectories, okay, with specific wave function, okay, which are just the time translated version of this original wave function that we started with. So if you want to prove this relation, right, that's what you have to establish. That if you multiply by this, multiply the left-hand side by this factor,
Hello,
to
sir.
the integral, and then evolve it in backward in time, it should look like well-separated particles moving along these trajectories.
Hello, sir.
Yes, go ahead, please.
I have a question here, sir.
Yes.
If we specify momentum exactly, then if we consider the spatial wave function that is uncertain, I think it spreads out to the whole space.
Yes.
Right? If we consider the wave functions of position wave functions, then those wave functions will overlap if we specify the momentums exactly.
Yes.
So in that context, how should we how should we remove this difficulty?
Yeah. So when I said describes n particles with momentum, okay, this was somehow a loose way of saying this, right? The precise statement is that the momentum space wave function is given by this. Okay. You see that here the momentum space wave function has a spread, right? It's not exactly pi equal to ki. Right? It's
Yes.
not a delta function.
Yes.
Okay. So once we use these wave functions, then there's no difficulty, right? Because these wave functions you have seen that when you translate to position space,
Yes.
there also it's spread out.
Yes. Yes.
It spreads out over a distance of root sigma,
Yes.
and that spread increases as root t also. But the trajectories get separated linearly in time, right? By taking t to be sufficiently large and negative, you can always make sure that the separation between the trajectories is much larger than the width of the wave function in the position space.
Okay, this is saved by that above Gaussian function.
Exactly, that's right. So this is not a correct, with a fully correct statement. When I say n particles with momentum, these are the central values of the momentum, right?
Yes.
There is a wave function that describes these particles.
And we may say that average values of the momentums.
Yeah, these are the average values of the momentum or the central values of the momentum. Exactly.
Thank you, sir.
Okay, are there other questions? Okay, so the key point that the key result that we'll be using, okay, is that you already know that this is true for the case n equal to 1, right? Because for n equal to 1, we have already seen that A in P1 dagger on the vacuum creates the single particle state correctly. Okay, and that's the information we're going to use to establish this, right? That when you take this product, okay, when you take the product of this times this and integrate, okay, it should describe states of this kind. Okay. So to do, oops, I don't know what happened here. Okay. So to do this, let's consider the ith term in the product. Okay, because these are just really independent products, right? They are of course all acting on the vacuum at the end, but let's look at the ith term in the product. So that's integral dq pi over 2 epi f tilde I pi times a in dagger pi. So because you are looking at only one term, I have just dropped the I index here, but P of course is the integration variable, right? So it doesn't matter. So let's analyze this. So to analyze this, we now write the expression for A in P dagger as A of T prime P dagger. Okay, eventually with the understanding that we have to set T prime equal to minus T times 1 minus I epsilon. And this one over root set. Now, I replace this A of T prime P dagger by its definition, right? Integral dq bar gp T prime r and then derivative of phi T prime r. Is this okay so far? Right? I'm just using the definition of A in dagger. Now we see that this of course has complicated derivatives. Okay. But what we can do is to perform the P integral first. Okay. So for that, let's first rewrite the expression for GP, okay, which is here. And now let's try to do the P integral first before we do the R integral, okay, and see what we get. So what is the P integral? Okay, it's integral dq P over, I think there is a square root of 2 EP from here, square root of 2 EP from here, dq P over 2 EP. Then you have this 1 over 2 pi to the 3 by 2 here. F tilde IP to the IP dot R minus I EP T prime. Now we are going to use the fact that F tilde I is a sharply peaked function around P equal to K, right? The width of course is root sigma, but you can take sigma to be as small as you like. So because of this sharp peaking, right, and this is a smooth function of P, we can just replace EP by EKI, right? Because this central value here is KI. Okay, so you can replace EP by EKI and take it out of the integral. So it becomes 1 over 2 EKI times this integral. And this integral, of course, by definition is Fi T prime R, right? You had done this earlier, and you are also found explicitly the form for Fi T R, right? Which is here.
Sir?
Yes, go ahead, please.
Sir, is an iota missing here in the definition of A dagger?
Yeah, maybe it is. Yeah, you are right. I think there should be an I here, right? Is that
True.
right? Yeah, exactly. Okay, but I will just carry along. Okay. Yeah, so there will be an I all through. Okay. So let's, but it will not be very important for what we are going to discuss. Yeah, so there should be a factor of I in these two equations. Okay, other questions? Okay, so I'll make this correction in the notes afterwards. Okay, so you now substitute this expression here. So what we get for this is the 1 over root z, which is here, right? And then 1 over 2 AKI that came from here. Okay, there's still a factor of I here. Then this integral dq bar, see P integral has already been done, so integral dq bar, this whole thing after you do this integral is becomes Fi of T prime R, and then this derivative del T prime of phi T prime R, and then you have to of course act on both sides. Okay, is this clear? Are there questions? So the point is that this operation you can do for every one of these A in dagger PIs. And every one of the A in dagger PIs can be brought into this form. So let's see what it gains us. Okay. So here I have written the same expression again. Here again with I missing in this. So now let's look at the expression for Fi T prime R. Fi T prime R, as you can see from here, is a wave function, the position space wave function is localized around R equal to Vki T prime. The width is 1 over root sigma. For sigma small, this width may be large, but it doesn't matter okay, it's still by taking T prime to be sufficiently large and negative, right, which is what you want to do, because you have to put T prime equal to minus T times 1 minus I epsilon, and then take T goes to infinity limit. So in that limit, however big the width is, these functions are all non-overlapping. So that's what I've said. Fi T prime R is a wave packet that is localized around R equal to Vki T prime. And as long as Ki and Kj are different, right, the wave packets for different i's are non-overlapping for large T. And now for each of these i's, right, it's the same time T. T prime is equal to minus T. So the phi and its derivatives, right, are all evaluated at the same time. And we know that from equal time commutation relations, right, that when there is a large separation in space at equal time, these operators all commute. So basically the phi's and the derivatives of phi that appears in the different A in dagger PIs, they all commute with each other, they act independently. So physically, you can think of it following, right? Imagine that we have some scattering that will take place at some point. We are observing this state at an early time, right? This minus T, where these different particles are, say, light year separated. Okay, the different operators that we have introduced, this combination, are separated by light years. Then what this operator does should be independent of what other operators are present. Whether those other operators are present or not, okay, the action of this operator should give the same state, okay, locally. Okay. And you already know that for single particles, okay, acting on the vacuum, it produces correctly, or the acting on the vacuum, this operator does produce correct single particle states, okay, with correct wave function. So basically the argument here is that because these trajectories are widely separated, each factor acts independently, okay, as if it's acting on the vacuum, because none of the other operators are present. Okay. And you have already seen that each factor acting on the vacuum creates the desired single particle state, right? And with the desired wave function, because that came from the previous result, right? That when we proved that A in dagger acting on a vacuum gives you the single particle state with this correct normalization. So now when you take the convolution of this with the FIs, it will produce a correct wave function. So this basically establishes that this product of A in daggers do create the correct in state. Because when you take the product of these A in daggers and take the convolution with these, it produces independent single particle states at far past with independent wave functions. Okay, are there questions, comments?
Sir?
Yes, go ahead, please.
Sorry, we are in the interacting field theory.
Yes.
So we cannot say that this A in dagger will create single particle state in the present time. It will create in far past and like, is it so?
That's right. Yes. So the point in the Heisenberg picture, right? T equal to 0 is when the scattering event takes place, right? So at T equal to 0, you cannot really say that these are single particle states. But in the far past, the in states have the property that in the far past, they have the interpretation of single particle state moving along independent trajectories, all approaching some common point in space-time where the scattering will eventually take place.
And why we are doing means why we're trying to keep it interpreting like single particle states, or because it is convenient to our understanding or something?
Yeah, because when you do the scattering, right,
Yes.
We have individual particles that we throw towards each other. They scatter and again produce some other state, which can be thought of as a superposition of independent particle states, right? Outgoing particle states. So the states with which we do our experiments are these in states and out states, right? We throw in states and we observe out states. Right? That's why this basis is the convenient basis. Right? This is just a particular choice of basis in which the particles act as free particles in the far past or free particles in the far future. Right? It is not possible to choose a basis in which the particles act as free particles both in the far past and in the far future.
Okay.
Right? I mean, you could have chosen other bases, right, where all these particle interpretations are not present. Right? This is a complicated superposition of these states. Right? Is there those in that basis? Okay, it is hard to translate that to what you measure in experiments. Is this point clear?
Yes.
Hello, sir.
Yes, go ahead, please.
Sir, here particles are identical, or can we take different particles?
Well, in this example, particles are identical, but we can certainly have different particles.
And also, I have a doubt: is these particles are scalar particles or vector or some kind of other particles?
Yeah. See, the point is, I have been discussing this in the context of high-force theory, right?
Yes, sir. Yes, sir.
So there, of course, all the particles are scalars.
Yes.
But the formalism that I have described, right, goes through for all kinds of particles, right? Okay. You may have to throw in some indices, right? Because vector particles, for example, will carry, besides this quantum number p, it will carry some polarization, right? Which tells us in which direction it's oriented in. But otherwise, the formalism is identical.
Okay. But here we are developing for scalar field.
Yeah. Here you have developed for scalar fields. That's why you have not introduced any other quantum number, for example, right? Any other polarization or anything else. But certainly this formalism is very general.
Okay. Okay.
Right? And when you do the other field theories, I'll not write down explicitly this whole formalism, but I'll just only quote the final results, okay, for the S matrix.
Okay.
Okay. Any other question? Okay. So we can do a similar argument to prove the other relation, right? That A in P acting on this produces this. And basically the argument is more or less the same, because after you take the convolution of with these products, right? Product of F tilde I Pi, basically different A and Pi Dagger factors act independently, right? Because they are acting at far away time, at time t minus t, right? If you express everything in terms of phi of minus t, they are acting at far away points in space. So A in of P acts on each particle separately. It doesn't, when it's acting on the first particle or in the region where the first particle is located, it doesn't care what other particle is present anywhere else in the universe. And because we have already established that A in of P acting on a single particle state behaves correctly, okay, gives the correct factor, that establishes that A in of P acting on a multi-particle state will also give the correct result. Okay. And I have not done it for the out states, but you can repeat exactly the same analysis for out states, right? Except that there you have to take the small t equal to capital T type plus capital T times 1 minus I epsilon, and then take capital T to infinity. Okay. But all the arguments will go through exactly as I have given here. Okay, are there other questions? So this basically is the end of, yes, go ahead please.
The way we have shown this, I mean, it seems that this relation is valid only in the limit when the particles are local, I mean, they have a finite spread.
Yes, you have to put a wave function, indeed.
Okay.
Yeah, because the point is, if you want to have no spread in the wave function, right, in the momentum space, then the particle wave function in position space will spread all over space, right, strictly, and vice versa. right? That's why you need a finite spread in the momentum space. Okay? But that spread can be as small as you like. Okay? Because if you go to sufficiently far past or sufficiently far future, then the trajectories keep getting separated, right? So for any small but finite width in the momentum space, you can always separate the position space wave functions, the overlap. We can always remove the overlap in the position space. Then you just have to wait for sufficiently long time, either in the far past or in the far future. So there is theoretically there is really no limit of how small the width can be, right? As long as it's a finite but small width.
Also, I mean, if this is the case, then what stops us from saying that the in state of multiple momenta is not the product state? I mean, I could as well have said that, use two Ain daggers on the vacuum and you will get a two particle state.
Yes, so I mean, if you use Ain daggers, right, they look like product states, but it doesn't buy you very much, right? Meaning, what will you conclude from there?
Yeah, I mean,
right? Yes, it's Ain dagger P1. I mean, that's what I have written here. Ain dagger P1, Ain dagger P2 on the vacuum, right? But it doesn't mean, for example, that it will remain like that forever, right? That's a good description in the far future.
Also, these two Ain daggers of two different momenta, they should not, they need not commute, right?
Well, the point is that they do commute, that we see from here. Because if you look at this expression, right?
Yeah, I mean, the way we are writing this multi-particle states, it seems that they are commuting, but I mean, I'm not sure.
Yeah, see, they commute in this sense that after you take the convolution with this, then they commute.
Yeah. Then it would not. It wouldn't matter the order in which we are applying these.
Exactly. Yeah.
Creation operators.
Exactly. Right. If you don't take the convolution, right, then they look like they don't commute. But if you take this convolution and that, however small the width is, then you see that, I mean, you can express in terms of phi of minus t. Yeah, maybe I should have said this also earlier, that I have been thinking, I've been stating the result by saying that you evolve it using Schrodinger picture, right? That, I mean, that's the way we are thinking of, that you take the state and evolve it using Schrodinger picture. Okay? What would the state look like in the far past or far future? Okay? You could have equally well have stated in a different way, okay, that we don't change the state, right? We keep the state as it is, okay, but try to express it in terms of fields at far past, okay, in Heisenberg picture fields at far past, or Heisenberg picture fields in the far future. It's easy to see that the effective wave function will be the same, right? The effect of evolving the state actually using Schrodinger picture or writing in terms of phi of minus t or phi of plus t, okay, has the same effect on the wave function. So what you are saying is that after you take this convolution, right, basically this product involves, okay, here it is, in terms of phi of minus t, okay, the corresponding wave functions get widely separated. Okay. And of course, phi at any common time, okay, have equal time commutation relation, that phi and phi dot commute. Okay. So this basically is saying that this factor, even though you could, I mean, if you try to express in terms of phi of 0, okay, it may look like they are not commuting. But by expressing this in terms of phi of minus t, okay, it makes it clear that they do commute.
Yeah, okay.
Right, so indeed they do commute, these operators.
So now that we are actually interpreting this Ain P dagger as some creation operator,
yes,
we can try and write this Hamiltonian in the sense that dq bar, DQP, EP, A dagger A with these A daggers, A in dagger and A in of P, and EP being the renormalized dispersion relation.
Yes.
That will give us basically a free theory, but with mass MP.
Yes.
Like,
But
yeah.
But that's not a full story certainly, because that is not given is scattering, right?
Yeah.
So the basis states which are relevant for scattering, right, are these states in the far past. But in the far future, right, the states that you observe are made by A out dagger.
Yeah, I mean that Hamiltonian is not a good description of the theory itself, even though we have some creation and annihilation of it.
It gives the correct energy, right?
Yeah.
If you have a multiparticle state, right, the energy of a multiparticle state, right, if you think in terms of asymptotic data, it is the sum of the energies of single particle states.
Yeah.
And so is the case for all the concept charges.
Yeah, so even though we can in this interaction theory also express these conserved charges, including the Hamiltonian in these new A dagger A, it is not meaningful for other things.
That's right, yeah. It is not meaningful for extracting physical information out of the theory.
Yeah, okay.
Because scattering involves transition between in states and out states.
Yeah. Also, the earlier thing that you were saying that particles may decay in cases where we have other multi-particle states with lower energy.
Yes.
That will also happen when the momenta, the A dagger P being the momenta we are applying.
Yeah.
That is very large.
No, it will not happen there because the theory is Lorentz invariant, right?
Okay.
You can always go to the rest frame of the particle. So just by giving large energy to a particle, you cannot make it decay. You can see it from kinematics.
Okay.
Because the point is, if you give it a large energy, right, large momentum, for example, then the final state particles also will have to carry that momentum, right? Total momentum has to be constant.
Yeah. Both of them cannot be maintained simultaneously unless we add more particles to the theory.
Yeah, I'll have more, well, not more particles to the theory. That suppose A can go into B plus C, right?
Yeah.
So, okay, if A cannot go into B plus C in the rest frame of A, then it is easy to see that A cannot go into B plus C in any frame, even if A has very large momentum.
Yeah.
The decay is not possible. Right?
Okay.
That's just a consequence of Lorentz invariance, right? Because you can always go to a rest frame of A and see that the decay is not possible. So if you cannot satisfy energy momentum conservation in one frame, it's clear that you cannot satisfy it in any frame.
All right. So this is not why, like when we say that particles of high energy are more likely to decay into low energy particles.
Well, we'll in fact see that they are less likely to decay into low energy particles.
Like, don't we say that when we like the high energy particles are unstable when
Well,
you
high mass particles are unstable.
Okay.
Not high energy, right? See, muon, for example, right, is an unstable particle. At rest frame, it decays very fast. But a very fast moving muon decays slowly, right? And that's just time dilation. That if the decay lifetime is fixed in a rest frame, right? Half-life is fixed in a rest frame, right? When the muon moves very fast, it will have a time dilation and it appears to be much longer lived.
I see.
And we'll also see it explicitly in one of the calculations later. Okay, when we calculate the decay, decay probability.
But don't we also say things like let's say there's a very fast moving electron.
Yes.
It can give off photons and lower its energy, moving energy.
That's accelerating electron, right? Not move. Just having a velocity doesn't help.
I see. Okay.
Because when the electron accelerates, it can exchange energy with the something else, right? Which is making it accelerate.
Is it the mu field?
Yeah, it's the mu field.
Okay.
Right, and that can produce photons, but not a electron that is moving at uniform speed.
All right.
Okay, are there other questions? Okay, yes, go ahead, please. Was there a question? Okay, so let me just say a few words about what we are going to do next. Okay, and then we'll continue this tomorrow. Okay. So the next question that we are going to address is the question of physical interpretation of the S matrix, right? Namely, how do you actually connect what you have done to what you actually measure in experiment? So in experiment, what we do, okay, is scattering, right? So basically, so there are two kinds of experiments. One is fixed target. The other one is collider, or you can also think of this as moving target. So in fixed target, okay, you have a stationary slab. Okay, say a stationary slab of material containing 5 particles with certain width, certain area. Okay, area actually we can take to be infinite, doesn't matter, because the particle is going to hit only a certain small area. And then you take another 5 particle and throw it towards the slab. It collides with the particles inside, and you observe what comes out. Of course, if you repeat the experiment many times in different times, in different experiments, you will get different results, because quantum mechanics is always probabilistic. So you can talk about probabilities of producing a certain number of five particles with certain momentum. And we will see that those probabilities that what you will calculate using this S matrix. So that's one kind of experiment. So the other kind of experiment, so this is what I've said, after the collision, what is the probability of finding certain number of 5 particles with certain momentum? So the collider experiment, okay, when a 5 particle collides with a beam of 5 particles moving in the opposite direction. So basically, you can think of this as the slab not being stationary, okay, but a moving slab. Okay. So a particle coming from one side, a moving slab coming from the other side, they collide. And again, we can ask what comes out of this, right? In a probabilistic sense, what is the probability of observing certain number of 5 particles going out to certain momentum? And so what we'll see next time is how to precisely calculate these probabilities. Because what the experimentalists measure are these probabilities, right? They do this experiment many times, and then they see what fraction of the time certain outcome comes, what fraction of the time certain other outcome happens, and so on. Okay, so we'll continue tomorrow with this question. So are there other questions?
Yes, sir. I had a question. Let's say we have, we described single particle states as those states which have the dispersion relation E square is P square plus M square.
Okay.
But and we could have multiple particle bound states which also satisfy this dispersion relation. So, how could we distinguish whether a state is a multiple particle state or a single particle state?
Yeah. So in general, there is no way to distinguish.
That's only the definition.
Yeah. So in general, there's no way to distinguish. When you are doing perturbation theory, then of course you can distinguish in the sense that the perturbative particles, right? If you have 5 to the 4th theory, for example, the fields which are created by the phi field are perturbatively. Those are the single particle states, right? And then you can have bound states of 2 phi's, right? In some theory which will be described as bound states. But in general, there is no way to distinguish between what are single particle states and what are multi-particle states. In fact, there are examples of quantum field theories, right, which are called the dual versions of quantum field theories, where in one version, right, one kind of particle, one set of particles appear as single particle states, the other are bound states. And in the other version, which is exactly equivalent, some other state, right, which are bound states in the first version, they appear as single particle states. And the single particle states in the first version appear as bound states. So indeed, in general, you cannot distinguish between single and single particles, the different kinds of single particle states, right? Elementary or bound states. But once you have a given formulation of quantum field theory, then typically the fields that states that are created by the fields, the elementary fields themselves, those are called the single particle. Those are called the elementary states, elementary particles, and then the rest are called bound states.
Okay.
But this is very much a theory. There is description dependent phenomena.
Okay. Yeah.
Sir, in theories like this, how is it possible to satisfy the same dispersion relation for the two kind of states?
Not the same dispersion relation, right? The mass will be different. Typically, in one description, right? Suppose you have written down a quantum field theory, right? You can have different kinds of single particle states, right? The elementary single particle states, bound states, and so on. Right? Like in QED, for example, you can have electrons, positrons, as well as positronium.
Okay.
Okay. So those will have the similar kind of dispersion relation, right? E square equal to square root of p square plus m square.
Yeah, but at the end, we are describing at least like theoretically the single particle states to have MP, which is the pole of G tilde P1 P2, right?
Yes.
So G tilde P1 P2 will have only one pole.
Or need not. It may have multiple poles.
Will it have poles corresponding to bound states also?
It could, right? It depends on whether the mixing is possible, right? So, for example, take electrodynamics. Okay, if you look at the electron Green's function, if the G tilde refers to the two electrons, the electron-positron Green's function, right?
Okay.
You will not see the positronium just by charge conservation, right?
Yeah.
Because the electron field will create a state with positive or negative charge, right? Positronium has zero charge.
Yeah.
But if you calculate, for example, the 2-point function of the photon, okay, there will be a pole corresponding to the photon, but the same 2-point function will also have a pole corresponding to the positronium.
All right.
Okay, it will not be seen perturbatively. Positronium you cannot see perturbatively, right? You have to use non-perturbative tricks. But in the full, if you could solve QED exactly, okay, then in the 2-point Green's function of the photon, you should see the positronium pole.
You say that we cannot do this perturbatively because
the bound states are not perturbative, right? You need non-perturbative techniques to see the existence of bound states.
Is that a general rule? Like,
yeah, that's a general feature that you cannot really see bound states in perturbation theory. Because
yes.
Bound states, you can, if you look at the structure of bound states, I think it becomes clear, right? If, for example, you take even in quantum mechanics, right, electron-proton system, if you could start with a field theory and started doing perturbation theory, right, thinking of the Coulomb potential as a perturbation,
yeah,
it will be very difficult to see bound states. Right? You have to actually solve the theory to see that there are bound states. You can see scattering. Right? Scattering you can do thinking of the potential as a weak.
Is it also like, this is not a proper justification, it's just a mathematical way, but in Feynman diagrams, we don't really have a like vertex representation of bound particles.
Yeah, so that's another way of saying. So in Feynman diagrams, if you want to see this, right, it basically comes from infinite iteration.
Yeah, it comes from what?
Infinite iteration of diagrams, right? You need infinite order diagrams to see new poles in the Feynman diagram.
Okay.
So this is a general feature that bound states you cannot really see in perturbation theory. May not be very encouraging, but that's the way it is.
Yeah, okay.
Okay, are there other questions?
Sir?
Yes.
Sir, when we say that we cannot apply perturbation theory and we have to go to some non-perturbative approaches, as we are studying this perturbation quantum field theory, do we have a subtle non-perturbative approach also? Or
Yeah, they are certainly non-perturbative approach. See, I mean, it's part of what we did in quantum field theory. We didn't use perturbation theory, right? Later on, we started doing perturbation theory, but there are certainly non-perturbative approaches to quantum field theories, right? Various techniques that one uses, right? Including numerical techniques, right? In lattice gauge theory, for example, people just put the quantum field theory on a finite lattice and then ask the computer to solve it. So there are non-perturbative techniques that one can use to go beyond perturbation theory.
And that non-perturbative techniques don't have these algebraic structure like what we have in perturbative theories, or it have?
Well, some part is it does have, right? The general features it will have. Right? The specific perturbation theory is not. It doesn't have. Right? I mean, you cannot write. See, the notion of the Green's function still exists, right? The notion of single particle states may still exist, even though the single particle states may be bound state. But the way we calculate the Green's function, that is perturbative. That's what doesn't exist in general, right? If the coupling is not too weak.
Okay, sir.
Is that okay, or we had some more confusion on this?
So it means that suppose at first we calculated the 2-point time ordered product of two fields over vacuum, the first basic thing we calculated.
Yeah.
So and that we are able to calculate because of this, because we can use perturbation at the first place.
Yes, but it still exists even non-perturbatively, right?
Okay, then we cannot it will be difficult to calculate, or we will use another methods to calculate.
You have to use another method to calculate the 2-point function, for example, or multi-point function.
Okay.
Okay, not as sum over Feynman diagrams. Okay. It's a sum over Feynman diagrams that is perturbative. That part you cannot do when the coupling is not small.
Okay. Okay. Thank
you. So
yes,
we can, in principle, like to some approximation, do let's say I have two electrons in a bound state.
Yes.
With each other. So I can for a specific class of states, I can use a spin one equation. I don't know the equation, but spin one Lorentz algebra representation to do quantum mechanics with it, right? Relativistic quantum mechanics.
Yes.
And to some approximate result, it might give correct answers also.
Yes, exactly.
So I can also perhaps do quantum field theory with a theory like this.
But that will not be quantum field theory of elementary particles, right?
Yeah.
That will be what we call effective quantum field theory, right? Where you think of the bound state as a particle.
Yeah.
And start doing quantum field theory. It may or may not be very useful, right? Sometimes it is useful, sometimes it is not.
Yeah, I was saying maybe it will give a pole in the Green's function in a perturbative sense.
Yeah. If you put that in, of course, it will give a pole in the Green's function in the perturbative sense.
Right? And that might be the mass of the 2-electron bound system.
Yeah. But that mass now you are going to put in, right? In the Lagrangian.
Yeah.
So that doesn't help, right? So you want to calculate, for example, what is the correction to the positronium mass, right? The relativistic corrections to the positronium mass, right? Which uses quantum field theory effects, right? Not just quantum mechanics. In quantum mechanics, you can go to a certain extent, but then there are quantum field theoretic effects, right? Which, for example, will correct the positronium mass. If you think of the positronium as an elementary field and put it in the Lagrangian, right? You have to also know what the effective Lagrangian is, right? If you want to do any calculation of the corrections.
But it might sort of will not give a good estimate of the correction to the positronium mass, but may give corrections to other things.
It could. Right. That's why the effective field theory is sometimes useful, right? You don't try to pretend that it's an elementary, these are elementary fields, but you can still write on the effective field theory of these particles. Sometimes it is useful, sometimes it is not.
So in a similar fashion, if let's say in our Lagrangian something is missing, some elementary, could you name a particle? Like
Yeah, some
elementary.
particle is missing, say Higgs particle is missing. Yeah.
Yeah, so it will give an incorrection, like it will miss out on some, the rest of the Lagrangian, the observations will miss out on some of the corrections.
Yes.
So isn't that then true for gravity as well? Because gravity is entirely missing.
Yeah. But the point is the effect of gravity are so small that it's not something that today's experiment can see. It is subtly missing. But today's experiment will not be able to see that missing part.
So by that logic, there can be a multitude of particles that are missing, but we are not seeing.
Certainly, yeah. So all you can say is that that there are no particles below this mass scale, because then you would have seen it.
Yeah, but the point regarding higher spin particles not having a QFT renormalizable version.
Yeah.
Like gravity, we are not including in standard model because we can't, because we don't know how to get meaningful results.
Yes.
But other particles, like hypothetically, let's say I have a spin 5 particle.
Yeah.
In principle, one can write down the representation theory, Lorentz algebra thing.
Yes.
Even though it might not fit into QFT.
Yeah.
And this particle, we are not simply observing in the sense its effect.
Yeah. I mean, if the particle existed and if it had low mass, you would have observed it directly, right?
Sorry?
If the particle existed and if it has sufficiently low mass, we would see it explicitly. In experiment.
Why do you say so?
Right?
But we don't know its contribution to the Lagrangian, right?
Yeah, but still, I mean, if the particle could be produced in experiments, right? So you can say, okay, its coupling is very small.
If it's small, then it should have come out.
Yeah, then you may not see it, right? Because the probability of producing this particle may be very, very small.
If the coupling is small or large?
If the coupling is small. Because S matrix has the coupling enters as the multiplicative factor in the S matrix, right?
Okay.
So if the coupling is very small, then the probability of producing a particle like that will be very small. So that could happen. But then you have to explain if it cannot be explained in quantum field theory. If you cannot write down a quantum field theory of higher spin particles, and if its coupling is small, then it's as good as not existing, right? If we discover such a particle, then you have to worry about it. In the context of quantum field theory, you can ask what are the consistent things that you can add to quantum field theory, which may not be observed. And those are typically particles of masses that are larger than what you have observed.
So, like strong enough coupling, but I mean, like not renormalizable things.
No, it can be renormal as well. Very heavy scalar, for example, right?
Okay.
A scalar of some 10 to the 5 TeV you will not have seen today, right? Because you don't seem to have energy is big enough to produce them, and their effect. I mean, you can say there can be indirect effects because they will contribute as the intermediate states in the Feynman diagram, right?
Yeah.
But because the propagator has 1 over p square plus m square, right? And if m is very large, that will also get suppressed.
I see.
So many times, in fact, if there are extra particles, right? Even if you cannot produce them, if you can see, you can see their effect in the as intermediate state, right? Because you see that their propagator gives some additional contribution to the Feynman diagram, and those you may measure.
Do we call these as virtual particles or something?
Yeah, you can think of them as virtual particles, but they are actually real, right? I mean, they are contributing to the Feynman diagram as virtual particles, but if you had enough energy, you could actually produce them.
Okay.
Okay, I guess the next class will start soon, so I should finish. So we'll continue tomorrow.